Hello friends and welcome to this video. In the chapter Wavelet Transform for learning the advanced digital signal processing, we have more convenience to learn Haar Wavelet here. So as in this chapter we have introduced to the two types of the functions to have completion of the Haar Wavelet theory. Those are the Har Scaling Function and next the Har Wavelet function that just now we have covered in the previous video. So as like for the Har Scaling Function, we had the translation operations as well as the scaling operations. It is also possible for the Har Wavelet functions. Now in this video we are going to make scaling over the Har Wavelet functions, and see the scaling can be of the two types, the time scaling and the amplitude scaling here. The scaling is the time scaling here, and that will give us a new functional space defined for the Har Wavelet function that we have introduced in the previous video. So let us begin with the topic to see the scaled Har Wavelet functions. So here we start with our topic, the topic titled Scaled Har Wavelet Functions. So let us have consideration of, first of all, the Har Wavelet function. The Har Wavelet function we had been denoting by psi of t here, and we know that for the time span 0 to 1 by 2 it is having the amplitude plus 1, and for the next time span of the equal interval 1 by 2 onwards up to 1 we have it at the amplitude level minus 1 here. So if we have the scaled version of this Har Wavelet function, or moreover the time scaled version of the Har Wavelet function, we can have the various versions at the different finer resolutions, we can say, with the help of this Har Wavelet function. So first of all, for example, we will go only for the dyadic type of the scaling here. So there should be of course a scaling factor here. So we will choose the scaling factor which is of the form having integer power of 2 only. So first of all, if we have the integer power of 2 is equal to 1, instead of having the original Har Wavelet function denoted by psi of t, we get psi of 2t. So 2 to the power 1 t here. So here you focus on the time interval. In the earlier case, for 0 to 1 by 2, it was the amplitude plus 1 for the original psi of t. When we make psi of 2t, you see the reduction into the time interval for the positive amplitude 1, and this is by the factor 2. So in short, it is halved here. Next to that, for the time span 1 by 2, 1 by 4, it should be 1 by 4 to 1 by 2. We have it equal to minus 1, and next to that we have it 0 elsewhere here. So this is the first version or the first time scaled version of the Har Wavelet function here. So now there should be a certain specific notation as we had in the case of Har scaling functions here. So for the Har Wavelet function, where we have the reduction of the time interval by the factor 2 here, we can see this to be a set of orthogonal bases, of course with the translation here. So psi of 2t minus k in general, if you denote for k belonging to the integer scale capital N here, we can have it denoted as w suffix 1 here. So w suffix 1 mathematically we represent as span for the k as a variable spanning for psi of 2t minus k here. So let us have one example with the help of the illustration, we shall discuss it. So few of the individual bases into the functional space capital W1 I will show you. So this is what the illustration here, and you see in general what we have talked of psi of 2t minus k, we have originally psi of 2t minus 0 you say. So the original representation mathematically expressed on the previous slide also. So we have it one amplitude for this much of the duration, and then minus 1 amplitude for the next duration here. So this is psi of 2t minus 0, or simply psi of 2t. We have next to that psi of 2t minus 1, psi of 2t minus 2, psi of 2t minus 3. So we have translation of the scaled version, time scaled version of the Haar wavelet function on the time axis. That is why we have psi of 2t, psi of 2t minus 1, 2t minus 2, psi of 2t minus 3. So this way, these are the individual bases. Why I call the basis? Because they are satisfying the condition of the orthogonality as well as the orthonormality. In the earlier video, already we have seen the functional space defined as capital W suffix 0, which is having a consideration of all the translated versions of the original Har wavelet function here. And now in this new functional space, we have the individual bases formed by the translation of time scaled Har wavelet functions here. So now what is the relationship between the functional space W0 that we have seen in the previous video and the W1 that just now we have defined? So as it is for the case of the Har scaling function, we had one set or the one functional space to be the subset of another here. So there can be a similar type of the question whether we have W0 to be a subset of W1, or in another wordings, can we have a representation of the signal if it is originally in W0 functional space by using the functional basis of W1. So that time we come to see the answer to be no. We are unable to have representation of a signal that is originally represented into the W0 functional space to be further re-represented by the use of the basis. Those are a part of functional space W1 here. Why it is? For that purpose, let us have one illustration here. So here it is the illustration you see. So originally we have psi of t, as I have shown on the right hand side here, Har wavelet function. So for 0 to 1 interval we have the amplitude levels for the equal intervals plus 1 to minus 1 here. And when we have the scaled version psi of twice t, here it is the representation. So we come to see that we have a difference as compared to the Har scaling functions. That is why we cannot have W0 to be the subset of W1 here. So here it is quite clear and important to note that since the linear combination of psi of 2t that you see on the left hand side and the corresponding translates cannot produce psi of t that we have shown on the right hand side of this slide. So no signal into the functional space defined as capital W0 can be expressed by using the functional basis of the functional space capital W1. So therefore we conclude that W0 is not at all a subset of the functional space W1. However, we can show that W1 is orthogonal to W0 here. See, the orthogonality sign will also be having the representation I will show you. So initially you first of all see, for the orthogonality condition we should have the multiplication of the two functional bases, and if that particular multiplication result or the product of the multiplication integrated over the complete time range results into 0, so that time we can say that the condition of orthogonality is satisfied here. So what we were representing the basis to be a part of either W0 or W1, you see this is one base psi of t here, and you see here psi of 2t. So psi of t and psi of 2t are from the different functional spaces here. Psi of t from w0 and psi of 2t from w1 here. Similarly, here it is psi of t from w0 and psi of 2t minus 1 from w1 here. So if you see the multiplication graphically also, you can validate it and integrate it over the complete time range, you will get it equal to 0 here. Now you see the illustration where the product or the multiplication of the functional basis we can show you. So here on the left hand side, initially you see psi of t, then we have psi of 2t. So psi of t from w0 functional base space, then psi of 2t from w1 functional space. Now you match the time axis, and here if you have multiplication of the two, the result will be shown in this representation. So as we have positive amplitude at level 1 in this operand and in this operand, you get positive amplitude here. And as we are having again positive but negative here, we get negative result here. So when we integrate it over the complete time range, we get the result equal to 0 here. Similarly, if you have psi of t here and psi of 2t minus 1, so here we have the scaled version as well as the translated version here. The multiplication here, you see the minus multiplied by plus, it will be a minus here. Negative part minus, again negative part, the multiplication results into the positive part here. So positive and negative on integrating on the complete time range will give us the product or the result, net result, to be equal to 0. So this will satisfy the condition of orthogonality. So as it was in the case of Har scale function, the functional space to be subset of another functional space, here it is not true, but here we have orthogonality of one functional space defined with the another functional space defined for the Har wavelet function here. So here we have seen that the area under the function, or when integrated on the complete range, which is the product of the two individual functional bases, it has resulted equal to 0. And further we have the orthogonality into the functional spaces represented like this here. So here we have the functional space W0 orthogonal with W1. Here it is the orthogonality sign here, orthogonality or the perpendicular sign here. So perpendicular means 90-degree angle here. So no component of one into the direction of the another, if it is there, we say they are perpendicular, and in the mathematical terms here it is orthogonal to each other. So the generalized relation between the various functional spaces defined by using the Har wavelet functions, if you talk, so we see that there it is orthogonality between w suffix minus 1 with w0, w0 with w1, w1 with w2, w2 with w3, and so on. So what summary we can have from all the learnings we have made so far for the Har wavelet function and the scaling function? So if you talk about the scaling function, the space spanned by the scaling function basis are into the nested form. So as it is having a subset relation, so v suffix minus 1 is a subset of v0, v0 is subset of v1, v1 is subset of v2, and so on. So theoretically we are representing up to the infinite levels here. So as it is subset, we are having the nested form relationship between the functional spaces here. Whereas if we compare the space that is spanned by the wavelet function basis, we find the orthogonality among themselves, and that is why this particular relation that we repeat, which we have already represented in above case here. So now as we have the Har scaling function, thereupon it was one point while discussing the functional space V0 compared to that of V1. So what was the missing component into the V0? That is why we had the need of generating the new functional space V1. So here we can answer this particular question with the help of one illustration. So in this illustration you see the solid line markings is the representation of a random staircase type of the signal, you can say. Not exactly the staircase, because there it is no linear rise or decrease here, it is a random way here. So now you see the functional basis phi of 2t. Whenever you come across phi, you just recognize that this is Har scaling function, and phi of 2t minus some constant or integer value, it is the translated version of the functional space that we have defined for the scaling function here. So this is what the signal, the amplitude levels are there in this particular diagram. So now as you see, it is not originally phi of t. Phi of t, if original it is there, so it will be having the constant amplitude equal to 1 for the time duration 0 to 1 here. We call it the Har scaling function. As we have reduction into the time interval by the factor 2, we have denoted it phi of 2t. So instead of the functional space V0, we have here the functional space V1 here. So if we try to have the signal represented into the functional space V1 defined here, so we get the mathematical representation. So signal can be denoted as f of t, and you compare on the previous slide the amplitude levels here. So we have 4 times phi of 2t added by 2 times phi of 2t minus 1. Next to that, 6 times phi of 2t minus 2 minus 2 times phi of 2t minus 3. Further added by 4 times phi of 2t minus 4, added by 6 times phi of 2t minus 5. And lastly, we have 2t of 2t minus 6, 2 phi of 2t minus 6, and added to 2 phi of 2t minus 7 here. Now here we can make one observation, that the signal segment into the first unit interval can be represented using the basis of V0 and W0, because what we observe, there it is a drop into the amplitude level also here. So in that regard, what we have in the earlier representation, 4 times phi of 2t added by 2 times phi of 2t minus 1 can be represented as 4 plus 2 divided by 2 times phi of t, further added to 4 minus 2 divided by 2 psi of t. So phi of t is from the functional representation V0, psi of t from the functional representation W0. So in short, we have 3 times phi of t added by psi of t. Now here we have the visualization of the same with the help of the illustration. So here exactly we are having the decomposition of the signal that we have represented earlier and also discussed to be from the functional space V0 by using the Har scaling function. And now here we are having the representation by decomposing into the functional spaces V0 and W0. So here exactly we are introducing the decomposition that is possible by the use of wavelet theory applied to the representation of the signals here. So as this step we have visualized here of decomposition, the similar fashion we can apply to the other steps here. So in the other steps, we have 6 times phi of 2t minus 2 minus 2 times phi of 2t minus 3 represented as 6 minus 2 by 2 into phi of t minus 2 added to 6 minus 2 divided by 2 multiplied by psi of t. So in short, we can represent it as 2 times phi of t minus 1 added by 4 times psi of t minus 1. And again, when we have the term 4 times pi of 2t minus 4 added by 6 times pi of 2t minus 5, we can get it converted to 4 plus 6 divided by 2, the ratio multiplied to pi of t minus 3. Further added by 4 minus 6 divided by 2 multiplied to psi of t minus 3. So this is equal to 6 times pi of t minus 2 minus psi of t minus 2. At last we can have 2 times pi of 2t minus 6 further added to 2 times pi of 2t minus 7, that is equal to 2 plus 2 divided by 2 multiplied to pi of t minus 4 further added to 2 minus 2 divided by 2 psi of t minus 4. So this is all equal to 2 times pi of t minus 3, and the ratio resulting into the value 0 multiplied to psi of t minus 3. So therefore the functional representation f of t will get the form that here we have f of t is equal to 4 times pi of 2t added by 2 times pi of 2t minus 1 added by 6 times pi of 2t minus 2 minus 2 pi of 2t minus 3 added by 4 times pi of 2t minus 4 further added by 6 times pi of 2t minus 5 added by 2 times pi of 2t minus 6 finally added by 2 times pi of 2t minus 7. So with the substitutions, here we have it 3 times pi of t added to 2 times pi of t minus 1, further 6 times pi of t minus 2 added by 2 times pi of t minus 3. Next to that we have the terms of psi added, that is psi of t plus 4 times psi of t minus 1 minus psi of t minus 2 added to 0 times psi of t minus 3. So here we could have the expression of a signal from the functional space defined as V1 in terms of the basis from the functional spaces V0 and W0, so that you can separately look at here. So the earlier terms are having pi versions here, next ones are having psi versions here, and pi of t and the translated version, not the twice or 4 times that way here. So this is from V0 and W0. So what we can call the relationship of having the functional space that originally V1 decomposed into V0 and W0, we can mathematically represent it with this particular symbol, that we have V1 equivalent to V0 with W0. In between V0 and W0 we have plus sign inside the circle. This is the sign to represent the complementary here. This is the sign to represent complementary. We can pronounce it as W0 as complementary space of V0 constituting V1. So here we have found out one thing that was missing into the V0, that made the V0 a proper subset of V1, and this was with the help of W0 here. So the decomposition at a finer signal into the coarser signals here we have seen here, and with the help of graphical illustration here we show, not the graphical here, simply the visualization of the earlier two equations here. So the functional space V1 with the coefficients as shown here has been decomposed to the V0 with these coefficients and W1 with these coefficients here. So here we are, I suppose this is the enough information to address what are the scaled versions of the Haar wavelet functions. So here I will conclude today's topic here, and by the next lecture into the same chapter wavelet transform, we shall be addressing the orthogonality condition of the Haar scaling as well as the wavelet functions. Thank you.